Hi everyone, my name is Haoran Yang, a PhD student at University of Technology Sydney. I'm the first author of the accept paper Dual Space Graph Contrastive Learning. Now I will present this work to you. Contrastive learning has attracted interest from the research community as a promising self-supervised learning method, which has achieved huge success in computer vision and the natural language process. Here, I would like to present a toy example to introduce the intuitions behind contrastive learning. Consider an experiment where subjects were asked to draw a picture of the dollar bill as detailed as possible. The figure on the left shows the drawing of subject made by recording what a dollar bill looks like from memory. Figure on the right is their drawing subsequently made with a dollar bill present. As is evident, the drawing made in the absence of the dollar bill is quite different compared with the drawing made from the exemplar. Despite having seen a dollar bill countless number of times, we don't retain a full representation of it. In fact, we really only retain enough features of the bill to distinguish it from other objects. Similarly, can we build representation learning algorithms that don't concentrate on pixel-level details and only encode high-level features sufficient enough to distinguish different objects? The answer is yes, and this is the core idea of contrastive learning. For any data point X, contrastive learning methods aim to learn an encoder such that the data point X is similar to the positive sample and different from the negative sample. As the formula shows, X plus represents the positive sample and X minus denotes the negative sample. The score function is a metric that measures the similarity between the samples, which will be determined according to the specific scenarios. In this case, data point X is commonly referred to as an anchor point. To optimize for this property, we can construct a softmax classifier that classifies positive and negative samples correctly. This should encourage the score function to assign large values to positive pairs and small values to negative examples. InfoNCE is a widely used loss function to achieve such a goal. Some researchers have introduced the concepts of contrastive learning into graph representation learning domain. For example, GCC, MVGIL, and GraphCell, which achieved state-of-the-art performances on various graph learning tasks. The key idea of graph contrastive learning is to construct proper contrasting pairs and try to learn the underlying important structural semantics of the input graph. However, existing approaches to generate contrasting pairs are quite limited. The majority of these methods are graph perturbations, including node dropping, edge perturbation, and attribute masking. As a result, these methods introduce noisy signals to produce cropped views, which degrade the model performance. Therefore, it's always a confronting, challenging problem to design effective ways to generate contrasting pairs. To avoid introducing too much noise, many researchers instead adopt subgraph sampling to generate positive samples. The intuition is that each subgraph has a unique focus on certain aspects of the graph semantics, and different subgraphs or local structures can hint the full semantics carried on the graph. Nevertheless, how to generate sufficient views containing unique and informative features is still an open problem, inspired by recent progress of geometric graph mining in the hyperbolic space, which has achieved satisfactory results under various real-world scenarios. We innovatively utilize the greater expressiveness of different embedding spaces, including the hyperbolic space and the Euclidean space, to generate multiple views of the input graph. There are two major advantages of the hyperbolic space. The first is that the hyperbolic space takes a smaller space to accommodate a given graph with complex structures, which means hyperbolic embedding has unique expressiveness compared to its counterpart in the Euclidean space. The most obvious uniqueness is that Euclidean space expands polynomially, while the hyperbolic space expands exponentially. Therefore, we can leverage that with much lower dimensional embeddings to represent a graph which will result in purer, compact, but powerful embedding spaces. Then let's step into details of the proposed methodology. The first is a subgraph sampling strategy. There is a major advantage of the hyperbolic space, which is that the hyperbolic space takes a smaller space to accommodate a given graph with complex structures. It means that the hyperbolic embedding has a unique expressiveness on graph hierarchical structures, preserving compared to its counterpart in the Euclidean space. For the Euclidean space, matrix in the Euclidean space is able to differentiate the relative distance among the data points, for example, satisfying the triangle inequality, and the superiority is evidenced by various famous clustering methods. Considering the different features, we propose to sample different subgraphs for embedding in different spaces. Specifically, for the Euclidean space, we choose diffusion sampler to acquire a more complete and unbiased view to serve as a skeleton of the input graph. For the hyperbolic space, we utilize community structure expansion sampler to extract hierarchical information and tree topology structures of the input graph. Both of these samplers are implemented by little ball of fur. As mentioned previously, different spaces have their own advantages and features. It's unwise to pick up only one of them to conduct tasks while discarding others. Instead, we could acquire semantics from contrasting pairs in different spaces via graph contrastive learning, leveraging advantages from both the Euclidean space and the hyperbolic space. To achieve such a goal, we conduct graph contrastive learning between Euclidean embeddings and the hyperbolic embeddings to obtain informative semantics of different views of the input graph in different spaces. Because there are different representation abilities among various spaces, however, embeddings in different spaces cannot be compared directly unless mapping one of them to another space in which another embedding is. Therefore, before comparing the embeddings in different spaces, we need to conduct space transformation. Specifically, we use exponential mapping mechanism to map the Euclidean vector to the hyperbolic vector. This is the overview of the proposed method. DSGC first adopts two different graph samplers to sample subgraphs for the two different spaces on all graphs. Then the generated subgraphs will be fed into different graph encoders and processed in different spaces. After obtaining embeddings of all the graphs, we conduct graph contrastive learning, which is maximizing the similarity between the Euclidean embedding and the hyperbolic embedding of the same graph, and minimizing the similarity between the hyperbolic embeddings of different graphs. To introduce the supervised signals into the model, the Euclidean embeddings of the labeled graphs will be fed into downstream predictor to predict the neighbors, and the cross-entropy loss function will be utilized to update the model. Next will be the experimental part. First, I will briefly introduce you the datasets and baselines we adopt to conduct the experiments. For dataset, we selected three publicly available and widely used datasets, which are MUTAG, rated binary, and collab. For baselines, we have two categories, which are graph neural network models and graph contrastive learning methods. GNN models include GCN, GraphSage, GAT, and GIN. Graph contrastive learning methods include GCC and GraphCL. Here are the comparison experimental results. Generally, the proposed DSGC method outperforms the baselines. Note that DSGC has much lower standard error comparing to the baselines, which shows that our proposed method is more stable when facing the datasets having different distributions. We also find that DSGC has more advantages on dataset collab. It shows that the proposed contrastive learning process is able to acquire more unsupervised signals, providing the model more informative semantics to achieve the best performances. We then study on the proposed method collaborating with different graph encoders for different embedding spaces to verify if it's feasible to use different graph encoders for further augment contrasting views to improve performances. The experimental results are shown in the figures, where the x-axis corresponds to the graph encoders for the hyperbolic space, and the y-axis corresponds to the graph encoders for the Euclidean space. The block with deeper color represents higher accuracies. According to the experiments, we found that the higher ratio of labeled training data, the better overall performance that DSGC has. But when ratio is low, it will be tricky to select different pairs of graph encoders for DSGC to achieve better performances. So choosing different graph encoders to produce contrasting views of input graph to conduct graph contrastive learning is indeed feasible and would be useful when label ratio is lower. In other words, when we face the real-world problems about graph contrastive learning lacking labels, we could carefully choose the pairs of different encoders to achieve better results. We also conducted a hyperparameter study regarding the hidden dimension of the graph embeddings. The most obvious uniqueness between the Euclidean space and the hyperbolic space is that Euclidean space expands polynomially, while the hyperbolic space expands exponentially. Therefore, we can leverage that with much lower dimensional embeddings to represent a graph in the hyperbolic space, which will result in compact but powerful embedding spaces. As the experimental results show, we note that smaller hidden dimensions like 8 or 16 do achieve more stable performances, which is that the average of the results of 10 folds and the standard error is continuous on the same dataset with different label ratio. But when hidden dimension is 8, the performance is unsatisfying. We think it's too small to maintain semantics of graph even if we have introduced the hyperbolic space. When hidden dimensions are large, such as 32 or 64, the results have not shown superiority. Note that the performances of DSGC with different hidden dimensions are not stable on the dataset collab, and the situation are more severe when hidden dimension is 32 or 64. Therefore, for DSGC, we should adopt a relatively small hidden dimension to have higher efficiency and better performances. In summary, we propose a novel graph contrastive learning framework, dual space graph contrastive learning, named DSGC, which first utilizes the different representation abilities of different spaces to generate contrasting views. It is feasible to select different combinations of graph encoders for different spaces to further reinforce the distinctions among embeddings of the sampled subgraphs. That's all about my presentation. Thanks for listening.